All right, so welcome everyone. Here we are. OpenSCAD is an amazing 3D design package. It's a language that lets you, it's not a CAD package exactly, it's a programming language, but a very lightweight scripty kind of language. It's not the fastest thing in the world, but it's pretty good. I have tried to do better, but that project failed. So yeah, the algorithm they use can sometimes get pretty slow, and it does have its limitations. So it's not designed for like really hefty stuff, unfortunately. It should be capable of that, and I tried to extend it, but it's hard. All right, so it's a C-like language, and the first thing you should know is that every simple statement ends in a semicolon, and there are curly braces. So if you're used to C or Java, you should be right at home. Unlike C, if you call a function like cube and you misspell it, it just whines at you that nothing happened because you called something that didn't exist. It doesn't exactly give you an error, it just sort of does nothing. So for example, if I make it a capital cube, right? I think the color changed here, but I'm not sure. But if I hit enter, oh sorry, you can't hit enter. Enter doesn't do anything. You have to hit F6. If you hit F6, it goes bong on my computer and it says nothing. And right down here I see warning, ignoring unknown module cube. So, and I don't know how to make this font bigger. I'm sorry about that. But you can all follow along on your machine doing the same thing. So, all right, number one, you need to get the spelling right. Oops. And number two, you have to get the semicolon. So if I hit F6 without the semicolon, notice the red dot shows up and it says error. You need syntax error. So yeah, put the semicolon in. And there we go. Now, if I click the mouse on this thing, I'm spinning it around the axis. But if I want to move it, then I think I use the right mouse. Yeah, the right mouse button. So this is button 3 on a Linux system. The middle button is the mouse wheel, which you spin to zoom in and out. Oh, I see. And if I press it down, then as I move, it zooms in and out more precisely, right? So spin to zoom in and out, right mouse button. Now, if you have a trackpad and you don't have a right mouse button, generally speaking, like 2 fingers on the trackpad will do this. I'm not sure. But yeah, that depends on your system, I guess. All right, so any questions on that, right? You can do a primitive. Here's a 3D primitive. You can spin it around. And let me fire up Chrome, actually. Okay, so I'm going to have Chrome in the background so that if we want to look something up. So let's just go OpenSCAD reference or something. Okay, so OpenSCAD, the documentation. So this is where all the stuff is on openscad.org. So that's pretty good. Any questions so far? Good. Let's see. Alex, Ellie, Eugene, Joris. I should remember to get everyone to sign up too. What? Yeah, particularly if you haven't signed up yet. Let's just get you to sign in. But I'll do it while you're doing your first kind of hands-on thing. I'll give you a few things to try out, and then while people are like playing around, I'll bring around a sign-up sheet. Okay, so cube, right? So there are 3 basic primitives. There's cube. I'll just comment that out so you can still see it, but there's sphere. Okay, so notice the sphere is centered on the origin, and the cube wasn't centered on the origin. In the cube, it was its corner on the origin, right? But that's because a cube has a corner and a sphere doesn't really have one. So where would you put the sphere if not centered on the origin? So that's why they do that. But if you want to, you could say, here, let me just clone it. Center equals true. So then you would center it. All right, so far we have 2 primitives, cubes and spheres. Now notice the sphere, it actually isn't a sphere. Just like in OpenGL, when we use the processing, you could see that a sphere is an approximation, right? Because there's no such thing as a sphere on a computer. Everything's polygons. Your computer is really, really fast. We'll do that next Monday. Your computer is really, really fast at drawing triangles, right? It's done in hardware. We went over Guru shading in that processing class. So we'll go over in OpenGL how the rendering pipeline actually works and all that. And so clearly they can render a sphere as a lot of triangles. That's the best way for them to do it. But you can see that it's, first of all, in this case, it's not just that you're drawing a picture of a sphere. You want to actually make it. I mean, here's an object that I made, right? So, right, in fact, you can see my son's name is like inside. So, and that was made in openscad, by the way. And by the way, the intention of this thing, and I was showing you this one, the intention of this thing was for me to make an ice cube maker. I thought this would be really cool for him, that like you make ice cubes with his name on it. Problem is, I very carefully designed. You see how the angle here angles out so that if you freeze water in this, if you put it upside down, it'll fall right out because it's got an angle. Look at any garbage can, any plastic injection molded garbage can, same thing. In order to get the plastic garbage can to go off the injection mold, they have to make it so that it'll slide off the mold. Nothing that's molded is made with straight sides. It's all got to have an angle. And here's another one I made with kind of a circular dish with a hole in the bottom. And that was to make believe it or not, a spherical ice cube. I actually worked. I had two hemispheres, and you could snap them together. You could fill it with water, and there was a little hole for the air to basically escape. And if you sealed the midpoint up well enough, it would actually hold water. But water would tend to leak out through that crack, so it was best to work with extremely cold water so it kind of freeze on the way out and seal itself. Anyway, so why am I mentioning this? This is made with OpenSCAD, but you've got a problem. If you put water in this, it locks up on the letters. It actually freezes into the letters. A couple things would happen. First of all, water would leak into the letters because the letters are formed in a certain way. It's complicated. That we'll do when we go over how to do slicing and how that stuff works, and hopefully Matthew will take you on a tour of the lab for anybody who wants to really do this in person and really try it out. So when you actually try to do this stuff, I'll try to hold this up to the camera really closely. You can see that the letters, maybe you can't see that. I can't see that on my screen. The letters are constructed with parallel lines, and water gets in between the parallel lines and starts leaking through the material. It's amazing, right? So if you just made a cup, it'll work. But if you try to get fancy and make a cup with these letters on it, and water intrudes and starts leaking through, it's kind of a mess. So there's two reasons that thing doesn't work. One, I told you water leaks through it. And the second one is that even if it didn't, water freezes into the areas inside the letter, and it won't let go. So what I needed to do was to make the letters also shaped trapezoidally, so the water would just come right off the letters, and it's not possible. I'm not in OpenSCAD anyway. If I have a letter, I don't know, let's just look at the S. Inside the S, water gets trapped. Inside the O, water gets trapped. And we'll talk about it. Anyway, but there's like lots of cool things for you to do. It's so much fun. All right, so we got cubes, we got spheres. Third primitive, cylinder. All right, now this time with cylinders, you got two parameters. You need to know what's the radius of the cylinder. You also need to know what the height of the cylinder. And with two values, I mean, you could just say, radius comma height, or height comma radius. That's the problem. I don't know whether this is radius comma height or height comma radius. One way to find out, just try it. Ooh, well, that's ugly. Okay, no, I take it back. There were 4 parameters, and I neglected. Yeah, I wasn't paying attention. Cylinder of 3 parameters: height, radius 1, and radius 2. Okay, so first lesson here of OpenSCAD. They cheat on the naming. It's not a cylinder, right? That's a truncated cone. So they lie a lot. Okay, so if I say the height is 20, and radius 1 is 5, and radius 2 is 10. then it looks like, kind of a garbage can. But bear in mind, it's not hollow. It's, it's solid. This is solid. All right, so there's your three primitives, and there's more complicated ones, but these are the simplest ones. There's a couple more. It's really a small language. We're going to be able to do it all in 1 hour, no problem. Okay, so again, you notice that this one is approximation. Each side is a flat surface, and it doesn't look like such a perfect cylinder. Well, it's not a cylinder at all. It's a truncated cone. All right, so they abuse the names. Let's do the same thing with a cube. You can say cube of, and this is in square brackets now. That's their syntax. That's sort of borrowed from octave. If you're going to give a vector, you do it in square brackets. So I could say 10 by 20 by 30. And notice now, okay, so they've used the names. That is not a cube, that is a parallel pipehead, but they didn't want to write parallel pipehead, they got lazy, so they called it a cube. But you can make your cube different sizes in each dimension. They're not consistent. Notice the cube, you have an array of dimensions, but with a cylinder, you just had three things. Oh well. All right, and what I find much better than just memorizing the fact that the first one is h, you just say r equals, I want the radius to be 20 and the height to be 10. Go. Okay, now notice in this case, the center of the bottom of the cylinder is on the origin because they couldn't put the corner on, there is no corner. And you didn't say center, so they just put it on the center of the circle. But if you want to center it, again, you could just say center equals true. Oh, come on. Center equals true. And now dead center is the origin. So any questions so far? Ron, Robert. Okay, cool. Bunch of people. Thank you for coming. All right, so there's our three primitives. Now, there are more primitives. For one thing, you could... A polyhedron's pretty complicated. We'll do that later. So you could make an arbitrary bunch of faces, but then you got to specify all of the faces, so it's kind of a lot of work. But let's just stick with these for now. These are the easiest three, right? And then all the rest of them are more complicated. So what can we do with this? There's a bunch of operations you need to know about. One, you can transform anything. So we did transformations last week and the week before in OpenGL type stuff. And for those of you who weren't here for that, no problem. We'll do it again. What three operations are there in 3D? I know, for those of you who were here, right? What are the three operations in 3D? What can you do to 3D shape? How about moving it around? What do you call moving it? Translation. Okay, good. Translate, right? So we got translation, and of course they have the translate function, so it looks exactly the same as OpenGL. I mean, not OpenGL, sorry. Processing. I love that the two are so similar, right? So translate, but it's not quite the same thing. Okay, so think of translate like an operator, just like it's a function, really, right? But think of it like a while loop in C++. When you say while something, it's while something like statement, right? And you put the semicolon here because you don't put the semicolon there because if you do that, you're saying while nothing, right? What you want to say is while whatever condition is true, do that statement. That's a loop in C++ or Java or whatever, right? Well, this is the same thing. You're saying translate the following. So let's just take one of the ones we did, the cube. I'm going to indent it because it's just like indenting a loop. And I'm going to say translate. Now, translate works with a vector. And this is borrowing MATLAB syntax. So square brackets means a vector. And there's three things in my vector, x, y, and z. So let's just say I translate it by 10 in the x, 20 in the y, 30 in the z. I love that it pops up the help. That's new. All right, and it moved away. Okay, so now if you remember, if I comment out the translate, okay, so a cube was normally on the origin. But if you translate it, you're saying go by, no, wait a minute, which way? I've lost track of which direction I'm in here. Okay, I think it's 10 in the X, 20 in the Y, and then 30 in the Z, right? But if you don't have to like look and guess, because down here, if you take a look down in the bottom left, it's showing you that X is to the right. I love that it shows you the little axis thing. But even so, it's so easy. Like, you spin it around, you're all confused, you lose it, and if you can't get it back. Okay, right now I have X is to the right, Y is into the screen, and Z is up. Right? Notice it's right hand rule. X to Y like this, and Z is, your thumb is in the Z direction. So this is like regular physics rules. But if you ever get confused, and they have some reset feature, I'm trying to find it. There, reset view goes back to the canonical original view. Oh, oops! Except the original view is the origin, and I asked for that feature, and they did it. So I was complaining that I would get myself all lost, like you end up like somewhere, and I can't even see it. I'm all confused. I said it'd be really nice if you just had a reset feature, and they did it. So very cool. Okay, so now let's just make this translate 10:00 just so we can see it a little easier. There we go. Okay, so you understand what that means. Now, what's going to happen if I put a semicolon? If I put a semicolon right here. So, if you overlearn the lesson of every statement ends in a semicolon, and you think that this one should end in a semicolon, it's not a statement, by the way. That's why translate applies to the next thing. But what happens if I do put a semicolon here? What's it's going to do? Yes, very nice. Okay, so I love that. When I have a student who doesn't understand like where semicolons go in C or Java, I take them to this and I show them. And when I do this, it works. And when I put in the semicolon, it doesn't work. There's something very visual about that people like. All right. So now suppose I want to translate two things. I want to translate a cube, and I want to translate a sphere. You'll notice the cube is translated, the sphere is not translated. Why not? What would it be in C++ or Java? You got to group them with curly braces, right? Because it only applies to one statement. If you don't put the curly braces, you were just translating that, and now you're doing both of them, and it works. Very cool. All right. Now, what happens if I say cube center equals true? Okay, so now they're both centered, but then I moved it with respect to the origin over by 10. So now, right, it's centered on the origin. It's centered on 10:00. Any questions so far? So we have three basic primitives: cube, cylinder, and sphere. I showed you that cylinder is actually not just a cylinder. You can do a truncated cone. You can specify 2 radii. So they abuse the language. It's not really a cylinder. And cube is not really a cube. You can give it 3 dimensions and make it, whatever shape. We just did the first transformation, which is translate. And I will basically just comment that out so you have a complete transcript of what we did tonight. I'll save it out for you. But I'm hoping now I'll give you these things quickly, and then you can I'll give you some challenge problems to make right here, and then you can go home and make something more substantial if you wish. Okay, so the next operation, translate, scale, right? So if I scale, you're supposed to give a vector again, and we're supposed to scale everything in the X, Y, and Z. So unlike processing, you can't just say scale by 2. You have to say 2, 2, 2, right? So if I say scale by 2 in the X and 1 in the Y and 5 in the Z, and I say sphere 10, go. Okay, so you see we can stretch it out, we can make it like an egg shape. Now you'll notice again, it's looking a little sad. It's not the greatest sphere, especially now that I stretched it. Some parts of it are getting kind of angular right there. So what we can do is the following. On any shape that involves a polygonal approximation, you can say facet number equals, and if you give it 30, it seems like what it was. Let's try 50. There we go. So if I say 50, you see there's more, it got a little finer. And if I say 100, it's going to get finer yet. Okay, but the problem is this is slow. Really, really slow. I mean, so far it seemed okay, right? But you haven't done any operations with these things. So, I mean, that's not like no problem to print this out. But if you try to take this and intersect it with something else and union it, you're going to start getting problems. So that's where their engine is kind of bad. But for normal kind of quick and dirty stuff, it's fine. And if you're willing to wait long enough, you can, generally speaking, do any kind of reasonable object. But yeah, it did seem a little pokey to me, and we tried to do better. And we wrote algorithms to do better, but putting it into production is a little different matter. Okay, so just pointing out, however, that even though you can do this, there's no reason to do scaling for a cube, because you could already scale the cube built in. So in other words, there's two ways of doing it, right? I could say scale 215 cube of 3, and it works. But I could just as easily have said cube of 6, 3, 15. Same thing, right? So all right, so far we've done translate and scale, and what's the last 3D operation? Transformation. And just like in processing, rotation can be around any arbitrary vector you can name. Now if I rotate a sphere, we're not going to see it too well. So what the hell can I rotate? Oh, we'll rotate a cylinder, all right? So let's do a cylinder first. Cylinder, h equal 10, radius equals 5. Go. There's our cylinder. All right, it's kind of lousy quality, so we could say facet number equals 50. There we go. Okay, so now let's say we want to rotate the cylinder so it's on its side instead of standing up. How would you do it? Rotate. So interesting, they're giving you rotate X, Y, Z. That's really weird. They should be giving me 2. Well, you're supposed to give it the axis. So let's say we say rotate around the x-axis. So now it's going to rotate around this axis, right? And the question is, I'm not seeing their help doesn't seem too good. You're supposed to be saying rotate around how much? So let's say rotate by 90. Let's see if that works. Didn't work. Okay, I got it backwards, which is not my fault because they didn't specify. I didn't see their help tell me. So 90, 100. There we go. Okay. So obviously rotating a sphere, not necessary, but rotating a cylinder can be necessary. All right, congratulations. You now know the 3 basic primitives. You know the 3 transformations, the affine transformations. Now, the other cool things you can do to this thing. Union, intersection, and difference. Now that's really awesome. So you can add and subtract shapes. So let's start with difference. Let's take the difference, and notice I'm putting it in curly braces because I need to take the difference of 2 things. So there's no point saying difference without curly braces. what's going to happen if I take a cube of size 30 and subtract from it a sphere of size 19? Can anybody predict for me what you're going to see on the screen when we do that? You're close. Well, the problem here is that the cube wasn't centered, so the sphere came out of the corner instead of the center. So you were right, Eugene. You have to like, how would you change this to make the cube centered? And now it'll be what you were predicting. Isn't that cool? Now, I don't have one of these handy at home, but I have printed this out. It's amazing. You can print this thing. Now, in the beginning, let's say 7 years ago, when 3D printers were kind of new, 7 to 10 years ago, this was kind of hard up here because this is not on top of it. You are squirting out molten plastic after all, right? So this part is easy. It just goes and goes around and it's building a square. So if you look at this from the top down, I mean, clearly, that bottom part we could print. But the problem is once you get up here and you're printing over air, how is this thing supposed to stay? What it does is it prints lines like over here and over here. And it's building its way up, right, on each side. And then when it gets over here at the very top, it has to jump very quickly and kind of lay a very thin thread. And then everything works. So if your printer is dialed in, it actually works. But having said that, not everything is printable. And that is one of the most fun things about this. You can envision anything in openscad, and but you can't necessarily print it out. And then you have to think, how can I make this so that it's printable? Let me show you an example. This thing is a hemisphere, right, with a hole on the top. I didn't have to make the hole, I could have made it. In fact, I think I put a little lip on it, like that, right? And the reason I put the lip on is because if I wanted to fill it to the top with water, the water would like kind of spill out and get all messy in my freezer. So I made that little extra thing so there'd be a little bump on the top, or at least so that it would completely fill without spilling. Anyway, so this thing is printable, right? I could start from the bottom, and I can just go around. That's the slicer's job, but so this shape is printable. So what shape is not printable? Let me tell you. Okay, if you build a shape like this, you're not going to be able to print it because you can support an arch by going up, 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 and then jump the last little bit. But if the arch is like really too long and low, you're not going to be able to do it. And worse yet, if you only have one side, then you're definitely not going to be able to do it. All right, so all printers have like this is the maximum slope I can handle. There are even these torture tests to show So like 45 they can usually do, and right around 50 or something, 50 to 70 they stop working. So I don't know the current state of the art in printers. It might be that some printers can go a little further than they used to be. They're very clever. What they try to do is squirt out a little bit of plastic and let it freeze, and then just keep going. But anyway, that's something you have to think about. All right. But okay, so we have now we did difference, and union is just like the union is just like combine everything. But by default, everything is a union. You don't even need to say union. You could just do two things and put them in the same print, and it'll work. All right, so you've got difference, you've got union, and you have intersection. So I've got nothing to do with union. I'm just going to comment that one out. Difference I showed you. All right, so let's do intersection. Give you another few primitives, and let you run wild and come up with some cool designs if you want. Intersection. All right. What the hell can I do with intersection? All right. How about? Oh, I don't have one on me. Wait, do I? Aha, I do. Just 1 minute. This is cool. Okay, the game of Go, an ancient Chinese board game. Here's a Go piece. It looks like a disc. This one's made out of slate. And you can see it's been ground into a very particular shape. It's like kind of curvy on each side, but flattened out. So it's sharp on the edge. It's not sharp, it's rounded, but it's not going to hurt you or anything. All right, so that's, can you make that shape? How could you make that shape? With intersections specifically. Any ideas? How could you carve out that shape between two other shapes? Look at the top of it. Doesn't that look like a sphere? But it's a really big sphere. Yeah, cool. Tell me what to write. Sphere 30, let's say. All right, now what do I do? Aha, so translate by how much? Okay, now one thing you should know, that's the radius of the sphere. So let's start with 0, 0, 15 and see what happens. Okay, you're sort of there, right? But it's not flat enough if you compare it to my shape, so you want to translate it differently. So what do you do? All right, let's try 20. All right, 25. What's going on? Seriously? How could I translate by 30? Oh, because that's the radius, right? Yeah, that's half. I could even remember it's only half. It's the diameter is 60, so I could do 50 even. Ah, right. Something like that. Now this isn't exactly right because the edge is very sharp here, but okay. Now this does look kind of lousy, right? Because we're only using a tiny bit of the sphere. So it's, we only have a few of the facets. It's not good. So we just have to up the facet number, right? And that's going to get slow. Let's see. I'll say $FN equals 50. Oh, I think instead of this, we could just say $FN equals 50 globally. And now, okay. So at the bottom of my screen, it was like grinding away. Oh, but it did it. All right. It's better, still not great. So if I do 100, so that's not just 100, it's not just twice as bad, right? That's 100 around the equator, 100 this way, and each facet is like 2 triangles, so we're talking about 4 times the number of triangles. Before it was like 50 times 50 times 2, now it's 100 times 100 times 2. It's like 20,000 triangles. And if that isn't bad enough, when it's doing the intersection between the two of them, it's trying to figure out, does every facet interact with every other facet? Which is a terribly stupid algorithm, by the way. And we could do a lot better. So anyway, I'm going to do it. And now it's growing and moaning. You can see this blue bar down there. Oh, it still did it. Ooh, but it crashed. Oh, that's nasty. Rendering finished, huh? Oh no, wait, I choose translate, not to translate. I meant FN. There's 100. All right, there we go. Okay, now it's sweating blood. See? It's done 200 out of 1,000, and then we're waiting. This is why I get pissed off at this, and I did a summer project where we tried to write one. Because that just shouldn't happen. It's not that slow. The problem is, their algorithm is that slow. It's an n-squared algorithm, and it's getting very, very bad. So there you go. There's our, doesn't look like a Go piece. Looks more like a flying saucer, but it's pretty cool. We could work on that some more. All right, so a couple more things, and then I'll give you free time to like try to do something fun. I'll give you a few challenge problems if you want to try to play this stuff. So 2D operations. You can do a square. You can't print a square because it's flat. So there's your square, right? That's like the analogous thing is a cube, right? So you've got a square, you've got a circle with radius 10 again, so this is going to be twice as big as the square. Okay, so it's centered on the origin. Well, there is no cylinder, obviously, right? Because square and circle are flat. But while we're at it, we can do polygon. That's the next level. So polygon of points. Okay, so you have a vector of points, but each point is a vector of x, y shape. So we could go, let's say, 10, 0 to 0, 20 to negative 6, 7, 8, whatever, to negative 20, 0. All right, to 0, negative 20. Let me just see what that looks like. Put a semicolon on it. Okay, so I made some funky, like, you know, pentagonal figure, right? 1, 2, 3, 4, 5. Yeah, okay, just to demonstrate. So yeah, they don't have a regular polygon or anything like that, but you can write functions and you can write one. Any questions so far? So we got a lot of cool 2D shapes: square, circle, polygon, and now comes my favorite stuff. All right, anything you got a flat? Oh, wait, font. That's cool. Hello. Oh, come on, where'd it go? Didn't like that? I'm forgetting stuff. I've got to like font. I've got to say like. Not font, text. Okay, text. Right, and you say what the font is. All right, so text. Hello. There we go. So yeah, you could set the font and whatever. But so there we go. We got a 2D shape. So all these 2D shapes, including your letters, can be extruded into the third dimension, which I think is so cool. So let's take this as an example. So if you apply the function linear extrude, and let's look at the first option. Very simple. Just the height of your extrusion is 10, and of course you apply it to the next thing, and cha-ching, right? Isn't that awesome? All right. Same thing applies, of course, to facet numbers. You can make everything better. So what they've done is they've taken a font in free type, imported it in, so they've got the two-dimensional shape of that font. I don't know how they pick how well to do it, but you can set the facet numbers up, and then once they have that, then they have a 2D shape which they then can extrude in the third dimension. All right, but let's say, you know, I was trying to do that thing with my son's name and make the ice cube thing. Can I make these things extrude outward so that, you know, they slope so the water doesn't get trapped inside? Yeah, the short answer is no. But I tried. Here's what you can do. You can say, whenever you do a linear extrusion, I mean, you know what? Let me not do it on this. It's too hard to see it. I'll do it on a simpler shape, and then you'll see what I'm talking about. All right, so let's just do a square. Square 10. There we go. Now, this is going to be a little boring, because you know what happens when we linear extrude a square. Linear extrude, height equals 10. What I'm going to have is a cube, right? So that's kind of boring. But look what you could do to it. Okay, you could start by saying scale equals 0.2. So I think by default, scale is 1. And then if you're saying the scale, you're saying well, how you end. So you're saying we'll start at size 1 and go down to 0.2, which means that it started with a big square and ended with a little square. Now notice, it slopes toward the origin because the corner of both of those things is on the origin. But of course we could center it. So we can make it kind of like, pyramid type deal, no problem, easy enough to do. In fact, to make a pyramid, what would I do? This is a truncated pyramid, right? How would you end up with a point? Scale 0. Isn't that awesome? Pyramid city. All right, so this one, if you put this at the bottom of a shape, water would in fact come right off it because there's nothing to get caught on, right? If I did it the other way, if I made the scale go to 1.5, so now if this was inside a container at the bottom of the container, then water could freeze in here, and then you couldn't pull it up because when you tried to pull it back, the water would hit that lip. So okay, but now imagine if I'm trying to take the letters hello and make them all slope like that. You can't do it because it only gives you 1 point to slope to. So I will try to demonstrate that. Linear extrude, my message hello, scale equal 0.5. Should do it. Okay, so you see the problem? Water is going to get trapped inside the O, and even though the side of the H is good, right? It's getting narrower as it gets to the top, but it's leaning over. So water's going to freeze in that and get trapped and probably rupture the thing anyway. But so you say, oh, but could I just do one letter? And could I center the letter? Oops, that didn't work. Okay, centering the letter isn't working, but if I translated the letter back so that the center of the H is so that it would be sloping in on all sides. So center equals true just doesn't work for this thing. How about translate negative 4? Let's try 4. I have no idea. All right, yeah, you're right. You can start to see that it's sort of working. And if I, instead of extra height, this is ridiculous height. If I made the height something more like 5 or 4. Okay, but the inside is still going to trap water. So, it's just a losing proposition. You just can't do it, right? What I would have to do, if you had the height be really small, and the scale of the letter is really big, and we properly shift it backward, yeah, even now, there's just no way. All right, so I know what I wanted to do, but just showing you, so it's good. It's good to understand that some things are just impossible. All right, so we've done 3D shapes, 2D shape, 3D shapes, 3D transformations, 2D shapes, and extrusion, but we haven't finished extrusion because there's some really cool stuff you could do. All right, my favorite, linear extrude. Okay, height. This is how tall you're going to make it. We've seen the scale. That's the ending scale. The starting scale is a 1. And twist equals 720. This is the number of degrees it's going to spin through while it extrudes. And then we're going to say square center equals true. Okay, but that's a terrible. Why did it do so badly? Linear extrude. All right. First of all, let me make it 360 for a minute. Okay, I don't think it liked my scale equals 0 thing. Let's try scale equal 0.5. And I could do more facets. Yeah, it's just not. It's not taking enough steps. I need to make it finer. So okay, linear extrude. So I can say facet number equals 30. There we go. That's better. Okay, so I stretch the thing out to it, but notice I've made a screw, right? I've twisted. I've made threads. You just take a shape. Now I think I also made it a little too tall. If we make it like height equals 10. Oh yeah, wait, how big is the square? Oh, that's my problem. I made the square. I didn't say the size, so it defaulted to 1. Okay, so if I make it 10, it'll get a lot nicer. There we go. Okay. So there you see, yeah, so it's got some strange defaults. You could literally, I've made screws, and I make the hole, I make the corresponding screw, and you can screw them in. And you have to sand them off a bit to really, it's amazing. It's so cool. All right. Now this is a solid hunk of plastic. What if you want it to be an empty hunk of plastic? Well, you don't have to make a solid square. So what you'd have to do is do a difference and compute something which is just a square ring, right? Like a border, and spin it as we did. So you could do a lot of cool stuff. All right, so let's see. So now I've covered linear extrusion. There's only a couple things left to do. I did fonts. There's also rotate extrusion. So this one is, all right, we're going to say the angle by default is 360. Let's assume we're going to rotate this thing by 360. Let's start by rotating a square of 10. I don't think it's going to work. All right, no, it did work. Okay, so kind of interesting. Let's comment out the rotate extrusion. You take that. Now I want you to envision spinning that on this axis, and as you spin it, you're gonna swing yourself through a cylinder, right? So I think that's what that just did. But it turned it, which is kind of odd. But all right, so if that's a cylinder, well, you already have a cylinder. So what else can you do with this thing? Well, how about just translating it somewhere? So translate by 10 in the x. Notice I only need 2 coordinates if I'm doing the 2D pin thing. So now you got like a square donut. So, you know, fun challenge. Can you make a regular donut? Should be able to, right? Can you make a donut where it's twisting as it goes? Like a kind of Mobius donut. I think you can. I haven't tried. So there's some cool little challenges for you. All right, so you go ahead. Okay, so I apologize that they're twisting this thing around, but they're taking the square, right? They're moving it to the right. They're rotating it by 90 degrees in a manner I don't understand, where they're rotating the cylinder at the end by 90 degrees. That seems kind of rude. They're changing the definition. So it should be like this as far as I'm concerned, right? But they basically move the square here. You see that this cross section right here is a square? And then they take that square and they rotate it around a circle. Here, you know what? Wait a minute. Let's do this. Let's rotate extrude angle equals 90. There you go. Does that make more sense? Now you can see the square. Isn't that cool? 45. Yep. But before, when it was rotating around the axis, so when I move it 10 away, you're rotating it around the axis, but you're now 10 away, so you get this donut-y thing. Yep. So, but it did rotate the square by 90 degrees, which is a dirty pool if you ask me. If you just say, just show me the square, that's not the square they're showing you, right? I'll demonstrate. If we just, here, I'll leave the translate on so you can see it, right? That's the square. But then they're flipping out, rotating it this way, which is dirty pool if you ask me, but that's what they do, okay? So that wasn't me, sorry. All right? Okay, so congratulations, you basically know almost the entire language. Now, there's two more things. They have this weird like interpolation thing called, oh god, what's Minkowski, that lets you like kind of like take the average between two shapes. So I guess I could just show you that, and then the last one is looping, and there's like functions and stuff, right? So yeah, you can construct programs out of all this. So that's right. You can make a module, which is like a function. So you can say module donut, and you can say I want the r, the radius of the donut, and little r, the radius of the thing, right? Or I could call this torus, right? So this could be a challenge problem for you. Can you write the code to make that go? You've given two variables, right? So there's my little instruction, right? So module is just a function, really cool, lets you build up these functions. And when you do that, let me just say, if I just did one, like just a circle of r like that, and go. Why is it no top level geometry rendered? Yeah, but I said circle. Oh yeah, sorry. No top level geometry because I didn't call the function. Right, so if you create a function called torus, you have to say torus of, let's say I want a donut that's 30 with a cross section of 10. Of course, it's not going to work yet because I just have the circle. So that's calling a function. All right. Let's see. I was going to show you Minkowski, so I think it's spelled there we go, Minkowski of, and you just give two shapes. So I think that one of the best examples is that a rounded rectangle thing. If I want to make a cube of 30, but I want to round the corners, I can, let's say cylinder radius equal 5. Okay, so there's Minkowski for you. Now notice what it did was it just added it. So your cube was 30 on the side, but when you add the cylinders to it, notice it got fatter because the origin is here. So you added a rounded corner here, and here, and here, and here. What is that, 40? Now you're like up at 30, 36 or something. So yeah, whatever. I said radius equal 5. I'm not sure how it did it exactly, but that's That's Minkowski. And last but not least, loops. Okay, so once you have the ability to write functions, you want to be able to write code in their functions. So this is really cool. You just say for x equal. Now you can just have a list. Like you say, I want to go x is 0 and 30 and 42. So you can do it like that, or you can do a list that's a sequence. Let's just start with that. Let's just say translate x00, and we'll do a cube of 5. So there's 3 cubes. So it's pretty cool. You could do that. It's really nice. I'll just do another one on the outside. For y equals 0, stepping 10 to 50. I'll nest the loops. Hey, what? Oh, right, I didn't say translate. Okay, so what it did was it just created 3 cubes, and then it created 3 cubes right over those first 3 cubes. So you don't see anything new. But if we translate it by xy, there we go. Okay. So what the heck can you do with this stuff? There is more stuff, but it gets increasingly specialized. So I think you can look through the manual if you want more. I'm just trying to think what other really cool features are there. I mean, certainly you can do all kinds of equations and stuff. But I want you to have fun with this. I want you to try some stuff out. Oh, it's already at the end of an hour. Man, God, that takes me a while, doesn't it? All right, well, I'll let you do it right now. I'll stay with you for a few minutes, and if you're interested in doing this with me right here, you can. And if you're not, you can go home and do it anytime you want. But let me just give you some challenge problems. Like the torus is a good one. Can you make a donut? That's rotating the circle. Can you make a... let me make a comment here. All right, a ziggurat. Anybody know what a ziggurat is? Google it. It's a Babylonian step pyramid temple thingy. Yeah, it looks like that. So that's a cool one to make. I mean, you don't have to make the stairs. That's a lot more work. But just making the steps. So it's like a stepwise pyramid. That's a cool one. That's like a loop with translate and jumping in. But definitely cool stuff. So ziggurat. Oh, this is a fun one. R2D2. Right, the Android robot. What else do I have for you? A pipe. Right, pipe of outer diameter, wall thickness, and length. Make me a pipe. That's a nice little function. Now the sky's the limit on the complexity of this stuff, right? You can, of course, once you write it, make a pipe, they're like, oh, make me a 90-degree bend in the pipe. Now make me a pipe that goes all. You can get crazy, right? But all right, I'll put down here gears and call it a day. Gear of teeth. Outer diameter. I don't know the terminology. There are libraries for these things. Let's call that tooth depth. All right, so these are fun challenges for you to do, and I'll just close by saying, is that a spur gear? I think that's just called a spur gear. Yeah, so it's a hell of a lot more complicated than that. If you look, they've got kind of very precise rounding so that they minimize friction here. Do they round it on the edges here? There's all kinds of potential things you could make as parameters. And there are OpenGL libraries to do exactly that, which is really cool. Notice that if you want to have teeth of a particular size, you can't make the gear any size you want, right? I mean, you have to, like, if you want to make 2 gears that mesh, that is a cool project, right? You want to make 2 different size gears, but you want the teeth to be the same size. So so. And of course, the cool thing is you can 3D print these things that actually make this work, which is awesome. All right, so I'm sorry, I always mean to do more interactive stuff, but it's very hard. We do an hour, and then I will stay here now for a few minutes, and anybody who wants to play is certainly welcome to do so, but I encourage you all. Matthew is ready to take you into the lab and like actually try this stuff out, right? So what you got to do, of course, is you don't want to go to the lab and be messing around with openscad. You want to like have some cool little thingy that you designed that you could print in a finite amount of time. To give you an idea, like this probably takes like 2 hours. It's like a lot of time. So you can, when you go, it's pretty like really small, right? And then you're going to need to use a slicer. We'll do the slicer. Is it tomorrow? I forget. I think I set it up for tomorrow. MATLAB tomorrow, slicer Wednesday. So on Wednesday evening, I'll just show you how to use a slicer. Matthew will in the lab show you a different slicer, but it's all the same stuff. So what you need is, we need to save this thing out. So the first thing is I'm going to save this out to Git, courses, workshops, openscad. Hey, you can see there's a bunch of files here from last time. I'm just going to call this like summary.scad. Okay. So now you just have like a summary of all the kind of base features you want to use. And if you've got it, here's a model. Suppose I wanted to print this model. I need to save this out. You're just going to say File, Export as STL. And that's going to save it as a shapefile. And then you got to take the shapefile and tell a printer how to print it. And that's what we'll do on Wednesday for anybody who's interested. All right, so export as STL. Yeah, I'll export it. Okay, summary.stl, save. There we go. And that's it.